So you've done your Moon Buggy Lab. Make sure that you've written out your procedure, exactly what you did. You have a nice data table. By the way, the graphs should be nice, and they should be clear, and they should not be these little tiny things. Nice and neat, incremented very well, okay, so that you can plot your points and try to interpret, and understand and analyze what's going on. And did you write a conclusion? Did you answer the question using your results? So that's what I want you to do for the conclusion. But I want to go over some of the data that was collected by Group 3. Okay, and so this is Garrett, Elijah, and Albert's data. And they had a very nice car that went a nice set of distances, very clean data, so I'm going to use that. If yours wasn't this clean, don't worry about it. But I'll show you underneath here. And let me zoom in a little bit. So they've got their procedure. Here are the materials, and here are the steps. We laid out the 10 meters of string, put the ramp at a height of 10 centimeters, place the buggy car on the ramp and release, measure how far it went, and repeat for 20 and 30 centimeters. Very nice, succinct procedure. I like it. Here's the data they collected. The height in centimeters, the distance traveled in meters, so 10, 20, 30, 1.35 meters, 3 meters exactly. One thing, if it's 3 meters exact, go ahead and put 3.0, so you know, hey, it was right on. It was right on 3.0. And then 3.9. Okay, so, and then when you graph the points, here's the graph. So everybody look at this graph. Now your graph, just graph your data, but here's what I like about it. All right, this is what's good about this graph. And for many of you, it's kind of not fair because, this is Garrett's graph, and he's in physics, and so is Dana. And so we do this all the time in physics. We start the year with collecting data and graphing it, and we learn how to draw graphs and stuff. But this is very nice. It's incremented 10, 20, 30. This is the height in centimeters, and he uses the letter H to represent height. And this is distance. And look at the data. At 10 centimeters, it was 1.35. Look how he incremented this. Very nice. This is in meters, right? So here's 1, 2, 3, 4 meters. And then he's got half meters in here. So 1.35 would be right here. And then at 20 centimeters, it was 3 meters exactly. And then at 30 centimeters, it's 3.9. So 3.9 would be right there. So we plotted the points correctly. And then we drew a straight fit line through it. Like, what is the best line through the data? So that's the one he picked. Now, this is what's called a graphical model of your car. What is a model? A model in science is like a model car. If you have a model car represents a car, doesn't it? If you have a little toy car, a little model car that you built, it has the same shape, it might have the same color, but is it a car? No, it just represents what a car is kind of like. Well, this graph is not your moon buggy car rolling down the ramp, but it does represent a part of how the car behaved. So we call it a model, a graphical model. It graphs what the car is doing. Now everybody listen up. This is really powerful stuff. So I'm not going to move on until I see every pair of eyes looking up here. Okay, so Nick, look up here. Okay, I want you to see this. A graph, a model does two things. It shows you what happened. And doesn't this show what happened really nicely? It also shows you if there's any patterns in there, right? Is there a pattern here? Well, it looks like if you plot these points, it looks like they make something close to a straight line, doesn't it? Now, a straight line is a pattern. We call that a linear pattern. And one of the things that I had Garrett do, which is above and beyond what I'm going to have the rest of you do, but he actually made a mathematical model. Do you remember in your math class, y equals mx plus b? Do you remember that? That's the equation of what? Y equals mx plus b is the equation of a what? Well, it's got a slope. It's got a constant slope. It's called a straight line, right? It's the equation of a straight line. So if you say y equals mx plus b, well, y is what your vertical axis is. But instead of calling it y, this represents the distance your car traveled. So we'll call it d. And then this is the slope of the line. Well, he did a rise over run calculation. Remember, slope is rise over run? Pick 2 points, do a rise over run. Got a slope of 0.1275 meters per centimeter. That means for every centimeter you lift it up, it will go 0.1275, or actually about 12 centimeters of distance. So this gives you a relationship of how the height will affect how far the car goes. And then what is our x-axis here? Our x-axis, our horizontal axis, represents height. So instead of using the letter x, use the letter h. So this gives us, and then what's the y-intercept here? When your height is 0, how far is your car going to go? How far is your car going to roll if you don't have any height at all? It's going nowhere. A distance of 0. So 0, 0. So this gives us a formula, a mathematical model for how the car behaves as it rolls down the ramp. So a good model, and this is a good mathematical model, and this is a good graphical model, they do 2 things. They describe what it is we observe. They show the relationships. They also have predictive power. You can make a prediction based on this graph. For example, what if I said, how far will their car roll if we raise it to a height of 15 centimeters? Well, let's look. Let's use their graph. 15 centimeters, go up here, read across, should be just over 2 meters, like maybe 2.1 meters. That's a prediction. Okay? If we lift that ramp up 15 centimeters, their car should roll 2 meters according to this graph. Now let's use the mathematical model. Does anybody have a calculator? Can you do this for me? Let's say that the height is 15 centimeters. So I'm just going to write in your notebook here. The distance, it will roll 0.1275 meters per centimeter of height. Now, how much height are we going to give it? 15 centimeters. Now, what happens to the units here? I have a centimeters here and a centimeters here. What's a centimeter divided by a centimeter? Centimeter cancels out, leaving a meter. Okay? Now, what is 0.1275 times 15? What do you get? Kids are helpless. 0.1275 times 15 equals 1.9, which is almost 2 meters. So I go up here, 1.9. So that's kind of interesting. I think it's just the way we drew the graph. But so about 1.91 meters. So the graph predicts about 2 meters. The mathematical model predicts 1.91 meters, which is pretty close to being the same thing. What we're going to do right now is we're going to do the experiment. And we're going to check and see if that prediction is true. But this is what we're doing here is called data analysis. When you make measurements and then you try to extract meaning from it. And the way you do that is you graph it, and then eventually we'll write mathematical models for it using that algebra 1 stuff, that y equals mx plus b that you did, to create formulas that give us predictive power. We can now predict things before they happen, and it'll be pretty close. So let's do the experiment and see what happens.